Vant hoff factor I. So Vant hoff factor is not a theoretical factor, it is a mathematical factor that is introduced into the formulas of the colligative properties like relative lowering of vapor pressure, elevation boiling point of solvent, depression freezing point of the solvent, and osmotic pressure, in order to correct the calculations of the molecular masses of the solutes which are participating in the either dissociation or association. Now let us see for this one how to calculate this. For non-electrolytes, I value is equals to 1. So that there is no change in the formula finally because I equals to 1. For electrolytes means for ions or solutes which participate in the dissociation, I value is greater than 1. And solutes which participate in the association, for association, I value is less than 1. Now let us see how these values are higher than 1 and lower than 1. And also you should remember that the value of I never be 0 or negative. I value equals to 0 means no particles are present. If no particles are present, that cannot be called as a solution. Only solvent it is. And negative particles does not exist. So that I value never be 0 or negative. Let us see how to calculate the Vant hoff factor using the formulas. Vant hoff factor says that to correct the molecular mass of the solute, normal molecular weight of solute divided by abnormal molecular weight of the solute. Usually we get the confusion among the, sometimes they use the normal, sometimes use the calculated, sometimes observed, experimental, theoretical. So abnormal, all these terms will give us confusion. So that I will give a small shortcut to remember all this. You always remember that normal is nothing but calculated. This is equals to theoretical. Abnormal or observed or experimental. So now this formula I can write down as a normal molecular mass is given and abnormal molecular mass. And here in the place of normal molecular mass, I can write down calculated molecular weight. Solute divided by observed molecular weight of the solute. Or also I can write down the theoretical molecular mass. Molecular weight of solute by experimental molecular weight of solute. So basically that you can remember. Now normal molecular mass by abnormal molecular mass, that is the I value. Now if molecular masses are not given but colligative properties are given, then how to use the molecular masses and colligative property relation? Already in the starting of the class we have seen that colligative property is inversely proportional to the molecular mass. So normal molecular mass is inversely proportional to the normal colligative property. Abnormal molecular mass is inversely proportional to the abnormal colligative property. See that here. Normal molecular weight is inversely proportional to the normal colligative property. Abnormal molecular weight of solute is inversely proportional to the abnormal colligative property. So in the place of normal molecular mass, if I substitute a colligative property, it comes to the denominator. And in the place of abnormal molecular mass, if I substitute the abnormal colligative property, it goes to the numerator. So that the final, in terms of the colligative property, the formula can be written as abnormal colligative property divided by normal colligative property, or this can be written as the abnormal means observed. Observed colligative property divided by next one is calculated colligative property. So let us try to see what are the colligative properties. So I value can be calculated. Relative lowering of vapor pressure, observed value divided by relative lowering of vapor pressure calculated. Similarly, I equals to elevation in the boiling point observed value divided by elevation boiling point calculated value. And I equals to observed depression freezing point divided by calculated depression in the freezing point. And also observed osmotic pressure divided by calculated osmotic pressure. So from this we can get the factor I value. And apart from this, there is one more formula to calculate the I value. That is I is equals to total number of moles of particles either after dissociation or association divided by total number of moles of particles taken initially. So this is the formula, and let us see how to calculate this I value for using the dissociation. So for dissociation, the thing is, this all whatever the mathematical calculations and formulas we are deriving, these shall be introduced into the finally colligative property formulas. Then we can get the clear picture how to solve the questions. So imagine there is a solute that is AN. It participates in the dissociation and produce n number of A particles. Initially I have taken the one molecule. Here 0 molecules are there. So before dissociation, this is molecules taken or before dissociation or association. I have taken one molecule, here 0 molecules. Imagine it's dissociated, alpha number, degree of dissociation, alpha particles are dissociated. So n alpha particles are produced. So total number of particles after dissociation. Total number means this one and this one. 1 minus alpha plus n alpha. So here alpha is common, so that we can write down that 1 minus alpha n alpha minus alpha. So that 1 plus n, it is equals to 1 plus alpha into n minus 1. Now let us take I value. I value is nothing but number of moles of particles after dissociation. After dissociation, these mean number of particles are there. So that I can write down that n minus 1 alpha plus 1. And before dissociation, only 1 is there. So 1. So this is the formula. That means I value for any particle that participates in the dissociation, formula is n minus 1 alpha plus 1. And if you want to calculate the alpha value, alpha is nothing but you send the 1 this side. So that I minus 1 by n minus 1, where n equals number of moles of particles after dissociation. N equals to number of moles of ions after dissociation. So let us take some examples to understand this. Imagine AB type of salt which dissociates into A plus and B minus ions. So number of ions produced is equals to 2. So I value is equals to 2 minus 1 alpha plus 1. So that is equals to I value 2 minus 1 means 1. So alpha plus 1. Now let us take the A to B type of the compound that participate in the dissociation, 2 A plus ions and 1 B 2 minus ion. Number of ions equals to 3. So I value equals to 3 minus 1 alpha plus 1, that equals to I value equals to 2 alpha plus 1. Next, A to B3. So 2 A 3 plus ions and 3 B 2 minus ions, N equals to 5. So I value equals to 5 minus 1 alpha plus 1, that equals to I value equals to 4 alpha plus 1. And here what happens if a solute is given like this? So imagine AX BY is given. So it gives XA plus Y plus Y B minus X, N equals to X plus Y. Then I value is equals to X plus Y minus 1 alpha plus 1. There are some solutes which confuse us. Let us take Hg2Cl2. If you take, it dissociates into Hg2 2 plus 2 Cl minus ions. In this case, number of particles are not 4 but equals to only 3. Then if it is 3 means this is applicable. So the I value equals to 2 alpha plus 1. Similarly, let us take the K4 FeCN taken 6, which dissociates in the water into the 4 K plus ions, and FeCN taken 6, 4 minus ion. Number of ions produced here 4 plus 1 equals to 5. So that I equals to 4 alpha plus 1. So like this, I value can be calculated for the ions that are going to ionic molecule that are going to dissociate. And regarding the alpha means per degree of dissociation. So this can be calculated as number of moles of molecules dissociated divided by total number of moles of molecules taken. So this is the degree of dissociation, but usually in the examination they give the percentage. Alpha value is always equals to 1, highest value is equals to 1. So you should not take the more than 1. 1 in the sense 100% dissociation is happened. Now let us see here how to calculate if percentage is given. If percentage is given, alpha value, degree percentage of dissociation is given instead of the degree of dissociation, then you see that given percentage value divided by 100. Imagine 60% of the molecule is dissociated. Imagine this is given as 60% is dissociated, rest is not dissociated. Then it is 60 by 100, that equals to 0.6. So try to see that the alpha value do not cross the 1. Highest value is equals to 1. That means maximum complete dissociation happens. Now the solutes which participates in the complete dissociation, if they say that complete dissociation happens, then N value equals directly I value equals to number of ions for complete dissociation. N equals to I. That means number of molecules, ions produced equals to factor I. Imagine NaCl dissociates into Na plus and Cl minus ions. Its N value equals to 2 because 2 ions are produced. If you imagine this completely dissociated, then its I value is also equals to 2. Similarly, CaCl2 dissociates Ca2 plus 2 Cl minus ions. 3 ions are produced, and if it undergoes complete dissociation, then I value is also equals to 3. So for complete dissociation, number of ions equals to the Vant hoff factor I. And this Vant hoff factor value So we may imagine that, sir, here NaCl and CaCO2, all these are strong electrolytes. Then why can't we take directly their N value is equals to I value in all the cases? All the cases, even these are whatever ions we are taking, these ions, we assume that they are participating in the complete dissociation, but complete dissociation do not occur on all these stages. When concentration decreases, that means when the amount of the solute increases, then the interionic distances between the ions increases, so that complete dissociation happens. So complete dissociation happens at the highest amount of the solvent or least concentration. That means highly diluted solutions. That is the reason why colligative properties are applicable to the highly diluted solutions. Now, for Vant hoff factor, I decreases by increasing the concentration. For example, if we take 0.1 m NaCl, 0.01 m NaCl, 0.001 m NaCl. In these cases, whichever is having the lower concentration, that has the higher Vant hoff factor. So Vant hoff factor is highest for the 0.001 m NaCl, next 0.01 m NaCl, next 0.1 m NaCl. Though the solute is same, but the percentage of dissociation is not same in all the cases. Here only some extent dissociates, here dissociation increase, here even increase, but it is not equals to the 2, even at this case it is equals to 1.97. So still 0.03% of the ions are not dissociated. So at highest dilution means all the dissociations are happened, means then N value equals to I value. So that value is usually mentioned in the question itself. They give whether they are participating in dissociation, or otherwise if they will give the degree of dissociation or percentage of the dissociation. So this is about the molecules that are participating in the dissociation process. Now let us see the ions that participate in the association. For association, so for association we can calculate the Vant hoff factor I as 1 upon n minus 1 alpha plus 1. If you want to calculate the alpha value, alpha equals to I minus 1 by n minus 1. What is n here? The n is number of moles of molecules associated. So how many molecules participate in the association process? For example, for a dimer, n value equals to 2. For a trimer, n value equals to 3. Trimer means 3 molecules participate. Example, if you see that acetylene, if it is passed through the red hot iron tube, then automatically it becomes the benzene. So earlier we have taken the 3 molecules, but it becomes a single molecule. Number of particles participating in the association is equals to 3. Though here completely chemically reacted, association in the sense some attractive forces are to be developed. So for association, this is the value. And the question arises here is, if in the case of the dimer, it is equals to 1 by 2. Let us see here, I equals to 1 by 2 minus 1 plus 1. So 1 by 2 minus 1 means minus 1 by 2. Next one, in the case of the trimerization, 1 by 3 minus 1 plus 1. Here alpha is there, alpha also has to be substituted. Now whatever the value it may be, whatever the n value it may be, whatever the alpha value it may be, the total 1 by n minus 1 alpha must be less than 1. Because even though it gives the negative value, that negative value must be less than the 1. So that's why I value is always equals to the positive value. So it never be equals to 0 or negative. Now let us see here how to introduce this Vant hoff factor into the colligative properties. So the colligative properties, relative lowering of vapor pressure, P0 minus Ps by P0 equals to Vant half factor I into mole fraction of the solute. Similarly, elevation in the boiling point, delta Tb is equals to I into Kb into molality. Delta Tf equals to I into Kf into molality, and pi equals to ICRT. So these Vant half factor values, whatever so far for association, this type of the formula has to be used, and that formula we have to introduce in these calculations, and later we have to do the calculation. And for dissociation, already formula was there. So using that calculation, first initially we have to calculate the I value. That I value has to be substituted in the respective question. If it is about the RLVP, here we have to substitute. If it is about the osmotic pressure, here you have to substitute. So after substituting the factor I, we get the exact answer. That is, it is nothing but Vant half factor is also known as the correction factor for this molecular weight of the solute. So dear students, I hope you understand today's class, and we shall meet in the next class. Thank you one and all.